Right then, today we're going to have a natter about volts, amps and watts. Basically, how electricity flows through a cable and what all that means. Don't worry if you're a bit new to this, I'll keep it nice and simple. No need to get your head in a spin over fancy jargon or over the top theories. Let's keep it straightforward. Let's start with the basics. Electricity. No need to overthink it. All you need to know is that electricity flows through cables, which are materials that carry electrical energy from one place to another. Think of a cable like a pipe. The inside bit, the conductor, carries the electricity, and the outer covering, the insulator, stops it from escaping or shocking you. Dead simple, really. Electricity flows in two main ways: direct current, DC, or alternating current, AC. Let's talk about DC first. DC is straightforward, it flows in one direction, like water running down a stream. Take a car battery, for example. You've got a positive terminal, usually marked in red, and a negative terminal, usually black. Hook up two cables to those terminals, connect them to something that works on 12 volts, and the electricity flows from the battery through the appliance and back to the battery again. Easy as pie. Now, AC, alternating current, is a bit different. Instead of the electricity flowing in one direction, the positive and negative sides keep swapping really fast. It doesn't actually flow like DC does. Instead, the energy vibrates back and forth. It's a bit like waves on the sea. The energy moves along, but the water itself stays where it is. AC is great for sending electricity over long distances, which is why we use it for most things like your sockets at home. Measuring electricity, volts, amps, and watts. Electricity is measured using three main units: volts, amps, and watts. Voltage is like the pressure of electricity. It represents the force that pushes electricity through a conductor. Using a water hose analogy, voltage is the pressure of the water in the hose. Amperage, amps, is the amount of electricity flowing through the conductor. Using the same analogy, it's the amount of water flowing through the hose. Watts measure the total power being used or transmitted. Watts are calculated by multiplying voltage by amperage. For example, if you have a 12-volt battery supplying 10 amps of current, the total power being supplied is 120 watts. 12 volts times 10 amps. Voltage determines compatibility. Voltage tells you what appliances can be connected to a system. For example, a 12-volt appliance must be connected to a 12-volt system. Similarly, a 230-volt AC appliance, common in the UK, must be connected to a 230-volt main socket. Voltage is crucial for ensuring compatibility between your power source and appliances. Amps and cable sizing. The amps of a system determines how thick the cable needs to be. Higher amps requires thicker cables to safely carry the electrical load without overheating. If a cable is too thin for the load it's carrying, it can overheat, potentially causing damage or even a fire. Using our water analogy, a thicker hose or cable can carry more water or electricity. For example, if you're connecting a large appliance, you'll need a thicker cable to handle the increased electrical load safely. Watts. Total power watts are simply the product of volts and amps. For example, a solar panel producing 10 volts and 5 amps generates 50 watts. 10 volts times 5 amps. Another solar panel producing 5 volts and 10 amps also generates 50 watts. The total power output is the same, but the voltage and amperage differ. This is important when designing electrical systems because higher amperage typically requires thicker cables, while higher voltage can reduce the current and, in turn, the required cable size. Batteries and energy storage batteries are rated in terms of their voltage and amp hours, AH. For example, a 12-volt battery with a capacity of 100 amp hours can theoretically supply 1,200 watt hours, 12 volts, times 100 amp hours of energy. However, with lead-acid batteries, only 50% of the capacity is typically usable to prolong the battery's lifespan, so the usable energy would be 600 watt hours. If you know the watt-hour capacity of a battery, you can calculate how long it will power a device. For example, a 1,000 watt-hour battery powering a 100 watt appliance will last for 10 hours. 1,000 watt hours divided by 100 watts equals 10 hours. Fuses and cable protection fuses protect electrical systems by breaking the circuit if the current exceeds a safe level. To size a fuse correctly, multiply the appliance's current draw by 1.25 to account for surges. For example, if an appliance draws 100 amps, the fuse should be rated at 125 amps. 100 amps times 1.25 equals 125 amps. Always ensure the cable is sized appropriately for the current it needs to carry. Undersized cables generate heat and can be dangerous.